Hello student. In this video I will discuss about the adiabatic expansion of an ideal gas for your third sem and what was that adiabatic process. Adiabatic process was that when a system or thermodynamical system does not absorb any heat, okay, but it can do some work by its using internal energy is known as adiabatic process. In adiabatic process, there is no heat exchange between a system and surroundings, that is Q equal to 0 or dq equal to 0. In this process, we will use a term gamma, which is known as ratio of Cp and Cv. Okay, the gamma is the ratio of heat capacity at constant pressure divided by heat capacity at constant volume. In an isothermal process, temperature of system remains constant, while in adiabatic process temperature must change because there is no heat absorbed by the system. So work done for adiabatic reversible expansion of an ideal gas. What is that? We know from the first law of thermodynamics, dq equal to d plus pdv, where dE is the internal energy change, pdv is the mechanical work done, and dq is the absorbed heat by the system. If absorbed heat by the system is equal to 0, if this is 0, then in adiabatic process 0 equal to Cv dt. What was the Cv dt? Because dE, what is the dE? That's mean Cv equal to del E del T by dE dt at constant volume. That's mean dE equal to Cv into dt. So in presence of dE, we can replace by Cv dt, and this is pdv, and dq equal to 0 for adiabatic process. For this reason, Cv dt equal to minus pdv. So this is also work done for adiabatic process. This is also work done for adiabatic process, though it is known as mechanical work. But here it is equal to dE and it is pdv. So dE equal to pdv, though pdv always we have seen that it was the path function, but since dE, this is dE equal to minus pdv, so work done. So dE is the state function, hence for the adiabatic process the work done is state function here, not path function. This is very important for your information and for your exam purpose. So Cv dt equal to minus pdv equal to work done by adiabatic process. So adiabatic process work done equal to Cv into T initial minus Tf, or minus Cv dt, that's mean minus T final minus Ti. Okay, and for an n mole it will be n Cv dt 1, and in presence of Ti, that is initial temperature and this is final temperature, then Ti from the ideal gas equation, Ti equal to Pi Vi by R and Tf equal to Pf Vf by R. This is the second form of adiabatic process work done. And Cv, and there is a R common, and this is actually W equal to here Cv by R, then R from Cv divided by Cv. Okay, then we can get 1 by R Cv, this is common term, into Pi Vi minus Pf Vf, or for adiabatic process Cv capital R equal to Cp minus Cv, and Cp by Cv equal to gamma. So Cp by Cv equal to gamma and minus Cv by Cv equal to 1. Okay, clear? So this is the equation, W adiabatic equal to, now if I take common Pi Vi, then 1 minus Pf Vf divided by Pi Vi equal to Pi Vi by gamma minus 1 into 1 minus Pf Pi into Pi by Pf whole to the power 1 by gamma. This is the third form of equation for adiabatic process work done. Okay, this is very important. And you know that Pf Vf to the power gamma equal to Pi Vi to the power gamma. From this side, this equation arises. Okay, because we can replace Vf by Vi equal to by this. That's means Pf by Pi equal to 1 by minus 1 by gamma. Okay. So this is the formula. So we can, or we have three forms of formula of work done for adiabatic reversible expansion of an ideal gas. This is very important for your university. Okay. Change of internal energy for isothermal reversible process of van der Waals gas. Already you know that del E del V at T equal to A n square by V square for ideal gas, for real gas, that's mean for van der Waals gas. We already proved in lecture 14 and 13. Now dE equal to A n square by V square into dV. Then integrating both sides within limit E1 to E2 and V1 to V2. Then we have delta E, that is from there E2 minus E1, that is delta E equal to A n square into 1 by V2 minus 1 by V1 from here, because this is 1 by minus 1 by V and limit is V1 to V2. And work done for the adiabatic reversible expansion of van der Waals gas, we know that adiabatic equal to minus delta E by dE equal to minus CV dt, that is minus CV dt means CV into T2, money T final minus initial, and if it is not taken in negative sign, then it will be initial minus final, plus this is for ideal and this is for extra work for van der Waals gas. Then for adiabatic process, total work done will be this plus this for real gas or van der Waals gas. From the above equation, we can say that WAD, that's mean adiabatic, for ideal gas is greater than that of the van der Waals gas. Why? Because in ideal gas there is only one term, and for van der Waals gas there is another term, that's negative. If we multiply this with the negative, then this will be negative. So from the above equation we can say that W adiabatic for ideal gas is greater than that of the van der Waals gas. It will be more negative. Now from the university question, this is for CU question, and it was already given by Calcutta University. So that the work done in adiabatic expansion, W equal to Pi Vi by gamma minus 1. From the 10 yards you can see it, this, where I means initial and F means final. Other symbol have their usual meaning. So answer will be this. Okay, answer will be this from here. Okay, so you should start from the first law and you should drive this equation. So that was a question from university. Relation between temperature, pressure and volume for ideal gas in reversible adiabatic process. Again, we know that from the first law of thermodynamics, dq equal to Cv dt plus P dV. For ideal gas and adiabatic process, dq equal to 0, this is Cv dt, P dV. Then Cv dt equal to minus P dV. And we know from the ideal gas equation for 1 mole, P equal to RT by V. So Cv dt, that means Cv dt equal to minus RT by V, here minus RT by V into dV, then this T will be here, then dt Cv into dt by T. Okay, if we put here, that will be like this, that is Cv dt equal to minus RT by V into dV. Okay, now this T by there, okay, and dV by V is there, and that is R. Clear? So this is the equation. Now integrating both sides within limit, considering Cv independent of temperature, that is, within limit, that is T1 to T2 dt by T minus R, V1 to V2 dV by V, here ln V and here ln T. So ln within limit, that is minus, this minus is there, this minus is there. So minus Cv ln T2 by T1 equal to R ln V2 by V1. This minus is here. Hence ln T1 by T2, if minus is in log, then we can take that it will be sign change, ln T1 by T2 equal to R divided by Cv ln V2 by V1. Then what happened? Just we arrange it, and ln T2 by T1 equal to, this will be on the log term, it will be power, that is V2 by V1 whole to the power R by Cv. It is in power. Now you remove ln from the both side, then it will remains here only T1 by T2, then, and from here V2 by V1 whole to the power R by Cv, and R means Cp minus Cv, then Cp by Cv equal to gamma, that is gamma, and Cv by Cv equal to 1. Okay, now if we cross multiply, then this is T1, this is V1 to the power gamma minus 1 equal to T2 V2 to the power gamma minus 1. Okay, equal to constant for ideal gas and reversible adiabatic process. So this is the very important relation, T V to the power gamma minus 1 equal to constant. Relation between temperature and pressure. Then what happened? Temperature, pressure. Again for ideal gas, PV equal to nRT, and for 1 mole gas, then PV equal to RT. Now PdV, if we differentiate both sides, then PdV plus VdP equal to nR dt. If for 1 mole, then n equal to 1. Then what happened? PdV equal to R dt minus VdP. Then for adiabatic process, dq equal to Cv dt plus PdV. So PdV means here R dt minus VdP equal to Cv plus R common. Here dt is common, so Cv plus R is common. Okay, dt, so dt common, so Cv plus R dt minus VdP equal to actually 0. Then what is this? R means Cp minus Cv. Then what is this? This is actually Cp. So Cp equal to VdP. Okay, total part equal to 0. Then Cv plus R dt equal to VdP. Then Cp dt equal to VdP. replacing V equal to RT by P, we get Cp dt equal to this by V replaced by this, then RT dP by P. Okay. Now again this is cross multiply Cp by T, that means Cp dt by T equal to R dP by P. So this is the relation. So this is the relation. Integration T1 to T2 dt by T equal to R Cp integration P1 to P2 this, and here again ln T2 by T1 and here ln P2 by P1. Okay. Here again you can write that replacing the ln term from the both side, we have T2 by T1 equal to P2 by P1 whole to the power. This is the common term. Okay. Or we can write here, problem, this is value will be ln T2 by T1 equal to R Cp R by Cp ln P2 by P1. Now this is R Cp, it will take in the power of this. Okay, this is will be power, and ln term from the both side will be removed. Clear? So what was that? That is T2 by T1 equal to P2 by P1 whole to the power R by Cp, or T2 by T1 equal to P2 by P1 whole to the power Cp minus Cv divided by Cp, that is T2 by T1 equal to P1 by P2 whole to the power. This is Cp by Cv equal to gamma, and this is Cp by Cp equal to 1, and Cp by Cv by Cp equal to 1 by gamma. Okay. So this is, if we altered this, then it will be negative, then it will be 1 minus gamma by gamma. Okay. Then T to the power gamma, cross multiplication, T2 into P2 to the power 1 minus gamma by gamma. Okay, and here T1 P1 to the power 1 minus gamma by gamma, and differentiating both side, dividing by the power in both side by gamma, then T1 to the power gamma P1 to the power 1 minus gamma equal to T2 to the power gamma P2 to the power 1 minus gamma, or we can say that T1 P1 to the power 1 minus gamma by gamma equal to T2 P2 to the power 1 minus gamma by gamma equal to constant. Okay, and this is the university question in 2018. Okay, then what happened here? The question was that 1 mole of an monatomic gas is allowed to expand adiabatically and reversibly from 22.7 liter at 1 bar and 0 degree centigrade temperature to a volume 45.5 liter. Calculate the final temperature and work done in this process. For reversible adiabatic process of an ideal gas, we know that the formula T1 by T2 equal to V2 by V1 whole to the power gamma minus 1. Then we just put here and we arrange this for T2 equal to T1 V1 by V2 whole to the power gamma minus 1. Then T1 was 273, V1 was 22.7 and V2 was 45.4, and gamma for this gas is equal to 1.66 minus 1. So 1.66 was the gamma. For monatomic gas, the gamma is constant value. So T2 equal to this Kelvin. So 172.78 Kelvin. And work done. What was the work done? We know the formula of the work done for ideal gas. N CV dt, that is N into CV T2 minus T1, and N is 1 mole and CV is 3 calorie per Kelvin per mole. Okay, and the difference of temperature is this. So that will be minus 300.66 calorie. Now, relation between pressure and volume, that is PV to the power gamma equal to constant, you already know, but we should prove it. Now for adiabatic process, dq equal to 0, so dq equal to cv dt plus pdv. Okay. Again, PV equal to RT for an ideal gas. PV, now differentiating both sides, pdv plus vdp equal to r dt. Again, dt equal to pdv plus r dt divided by r. Now, replacing dt, this is dt, replacing dt from the first law equation, 0 equal to, this is dt, again add dt. Sorry, there is a pdv plus r dt, r common, sorry, there is a problem, v dp, v dp. That was it. Now, replacing dt by this equation, in equation here, this is the 0 equal to this. So now replacing dt from the first law equation, 0 equal to, 0 equal to cv r, this is dt plus pdv plus pdv. Okay. Now cv plus r, cv plus r, cv plus r divided by r, pdv equal to minus cv by r vdp. Again, cv plus r equal to cp, then rearranging cp dv by v equal to minus cv dp by p. By rearranging, this is cp, and from the both side r is 1. On integrating both sides within limit p1 to p2 and had v1 to p2, then we have actually minus gamma, cp by cv equal to gamma, so minus gamma ln v2 by v1 equal to ln v1 by v2. I had from ln p2 by p1, that's been here, from here it is ln p2 by p1, and from here it is minus gamma ln v2 by v1, and this gamma is in the power, and if minus is replaced by plus, then it can alter. So ln v1 by v2 whole to the power gamma. Now replacing the ln from the both side, then we get p1 v1 to the power gamma equal to p2 v2 to the power gamma, or p3 v3 to the gamma, or p v to the power gamma equal to constant. So this is the relation between p and v. And case study. What was the case study? That was the problem from University Calcutta. Case 1. What happens if we consider gamma equal to 0? If gamma equal to 0, that's mean, and gamma equal to 1 and gamma equal to infinity, then what happens? Then what will be the relation? Now, for reversible expansion, we are having the pv to the power gamma equal to constant. Then differentiating both sides with respect to v at constant temperature, we get del pv to the power gamma del v. If this is constant, then this is maybe psi, no problem. If it is constant, then it will be 0. Okay, then it will be 0. Then you can say the derivation of this with respect to v, at first p constant, del v to the power gamma by dv, plus v to the power gamma constant, del p del v equal to 0. Then del p del v equal to actually slope. What is the slope? If we consider the graph pressure versus volume, pressure in the y-axis, v in the x-axis, then p by v equal to slope, that's means dp by dv equal to slope, then slope will be negative. That's means gamma, because you know the dp dv equal to, it will be minus p by v. How? If gamma equal to 0, then dp dv equal to 0. For gamma equal to 1, dp dv equal to p by v. And for gamma equal to gamma by gamma equal to constant, then dp dv equal to minus gamma p by v. Then this is very important, and it is university problem. Then this is the p-axis, this is the v-axis. If gamma equal to 0, then pv constant. Okay, that's mean p with the change, this will be straight line. If gamma equal to 1, this is the line, this is not straight line. If gamma equal to gamma, this is the ভ্যালু। অর্থাৎ তোমাদের এই ব্যাপারটা তোমাদের মনে রাখতে হবে যে এই গ্রাফটা তোমাদের ড্র করতে হবে, যে স্লোপ কিরকম হবে। সে আমরা দেখতে পাচ্ছি নেগেটিভ, এটা একদম 0, এটাও নেগেটিভ অবশ্যই, অ্যান্ড এটা স্ট্রেট লাইনের মতো, আর এইটা কিন্তু সেটা প্যারাবোলিক নিয়েছে। ওকে, সো লেকচারটা শুনবে, এটুকু পুরোটাই কভার করবে। তারপরের দিন ইউনিভার্সিটির এই কোশ্চেনগুলো আমি করাবো।